Good morning, everybody. Okay, thank you, Del Watson. Thank you, Matthew, Jason. All right. Thank you, Corey. Well, I was talking about sequences and series. Um, and one of the reasons we are interested in sequences and series would be the power series. Now, here is a quick review of power series and um, why we really are interested in power series. And later on, of course, power series and will be used in uh, that residue theorem, and we will do a lot of integration by finding residues. Anyways, we will get back to those areas later. But here is what a power series is. A very, very quick review to give you a better feelings about this important topic, by the way, very important topic. A power series looks like this, which we call it power series centered at Z naught. All right. After all, this is a series, all right? It is a series, but has the sort of feature that this A sub k is fixed, the center is fixed, but Z can change. All right, this Z can change, can take over different complex numbers. Then the question is, for what values of this Z this series converges? Well, I gave you a bunch of examples. Here is just, for example, A sub k, all right? This sequence right here. And the center is 1 plus I. So Z minus Z0, right? Minus that center. All right. So the main tools, I would say, the main tools that we have in dealing with power series for the time being is that generalized ratio test. For example, here, if you call the whole thing B sub k, here's the whole thing, right? This is the series, call the whole thing B sub k. Then applying the generalized ratio test, you got to form this quotient B sub k plus 1, which is this portion, divided by B sub k, and dividing by B sub k is multiplying by reciprocal of B sub k, right? So by reciprocal of this guy. You do the simplification, and this is what you get. So the generalized ratio test works this way. After you form this quotient, the modulus, then you take limit as k approaches infinity. And whatever the limit, in this case, limit, of course, as k approaches infinity, denominator, gets as huge and numerator is fixed. So you get 0. And that is what we call L. If L less than 1, the original series, all right, converges absolutely. If L is bigger than 1, it diverges. Okay, L equal 1, no conclusion. So here is the beauty of this generalized ratio test. By working on that limit of the quotient and discussing the value of L, we can make a judgment on this infinite series. So please distinguish these two things. Here is a sequence generating this series. By examining this generating sequence, we are making a judgment on that infinite summation. Oh, that's the very important part of the series. Anyways, this series converges everywhere. So no matter what Z, it converges all the time. Then I gave you another example. Here is another series. Let's see. Let's see if I can make the thing sharper. Oh, well, maybe I need more light. Make it better. It's a little bit better, not much. Okay. So here's another series. Again, you call this is the generating sequence. We look at this, we examine this, and make a judgment on this right-hand side, on this infinite series, infinite summation. So I discussed that example last time, but it doesn't. It helps after you read the topic and did a few examples. The review sometimes helps a lot. So here, you call this generating sequence A sub k, the whole thing. Then you form the quotient A sub k plus 1 over A sub k modulus. This is what you get. And if z is not 0, then the limit as k approaches infinity is infinity, all right? So this series, here is your L, is bigger than 1. So because of this, that is bigger than 1, the original series, this one, this infinite summation, diverges, all right, diverges. Good. Well, here is another one. We discussed this one. As I said, this is a quick review. So this is, yeah, here is another one. So here is the generating sequence. And we are dealing with an infinite summation. But as I said, the beauty of this ratio test is by examining this generating sequence, we make judgment on that infinite summation. So call this one A sub k, form the quotient ratio test. This is what you get. As k approaches infinity, of course, This is 1, so you get Z. This is your L now. So the limit of the ratio test is Z. If this L is less than 1, this series, that infinite series, converges absolutely. But if Z is bigger than 1, the modulus of Z bigger than, it diverges. All right. So that inspires us to, so when Z is less than 1, which means within this disk, you choose Z here, then that infinite summation converges absolutely. And when it converges, of course, it produces a number, right? Okay. This is called the disk of convergency. And this radius, which is 1, is called radius of convergency. All right. Okay, good. And I gave you a bunch of examples to make sure that you feel comfortable in working with power series. Here is another one we discussed. So again, this is the generating sequence, all right? This is a sequence, but we want to make a judgment for that infinite summation. You use ratio test right here, and the limit when n approaches infinity in this case is this one. This is your L. If this is less than 1, the series converges absolutely. And if it is bigger than 1, diverges. But this less than 1 means all the points in a disk centered at 2i with radius 1. So every point in here, in this inside the disk, if we choose a point inside the disk, this series converges absolutely. But if you choose a point outside, it diverges. Okay? Now, inside the disk of convergency, this power series behaves very well, behaves like a polynomial. And that's what we like, behaves like a polynomial. All right, let's see what else I have discussed last time, going step by step. So here is another example in which we wanted to find radius of convergency, and we did. Again, we considered the generating sequence, called it AN, formed the ratio test, generalized ratio test. And here is a comment that we cannot, even in this case, we can use the n-through test. That's true. But since I am sort of concentrating on ratio test, so why not? Let's use the ratio test. The limit is this. This is the L. If this is less than 1, this series converges absolutely. But what is the meaning? What is the interpretation of this be less than 1? The interpretation is that you multiply by 4 and take third root. That means modulus of z has to be less than this number. So that is the radius of convergency. The center, of course, center is 0, all right? So that is the radius of convergency here. The center is 0. Radius of convergence is third root of 4. You choose any point inside. The power series converges, otherwise diverges. And any comment, any questions so far? As I said, I really would like you to feel comfortable working with this power series. We need this power series later on. Okay. No question? Good. So what else? Then I told you that this power series we like because within their disk of convergency, they behave like a polynomial, right? They behave like a polynomial. And in fact, if you have this power series within the disk of convergency, it is a continuous function. It's a beautiful function inside that disk of convergency. It also has derivative, right? It has derivative. And how do we take derivative? Just term by term, all right? Like what we do in polynomials. Differentiate term by term. And in fact, it's the integration also will be term by term. And nice thing about it is that the integral and the derivative will have the same radius of convergency as well, all right? So that's good to know. Then yeah, this is sort of justifying that why derivative has the same radius of convergency. And then I talked about this important, it's very important series called geometric series. And this geometric series converges if and only if modulus of P is less than 1, all right? Modulus of P has to be less than 1. And we use this one in the proof of Taylor series, but for the time being, I want to talk about something else. Okay. A lot of functions, they don't come in the form of power series, like this one, right? Like this one. They don't come in the form of power series. Then the main question is, can we find a power series representation of this type of functions? And the answer is, oh yeah, we can, but the function has to be analytic in a domain. And that is when we apply the Taylor series, all right? We apply Taylor series. But suppose this function has a power series representation. Okay, here. Suppose we have this power series representation for this function, then the question is, can we have two different power series representing this function? The answer is no. If there is a power series for this function, it has to be unique. Okay, it has to be unique. Now, here is an example where the center, I mean, it's just written in the powers of z. It could be in powers of z minus alpha, but let's look at this one. This z, z squared, z cubed, zn, and so forth, those are always there. Those are the variables. A power series will be determined by these coefficients, right? By that coefficient of z. In order to show that the power series representation is unique, you want to say that, all right, there is no way that we can have a different number here. Why? Here is why. As I said, within the disk of convergency, this is a very beautiful function, continuous, has derivative of every kind. So you evaluate this function at 0. Let z be 0. So f of 0 on the left, on the right, all these terms will vanish. You get a0. So here comes a0. It is just the function evaluated at 0, right? And when you evaluate the function at 0, no way you can get two different results. So a0 is unique. Next, you take derivative. Derivative of this function, as I said, in the disk of convergence is right here. You take derivative term by term. Derivative of this constant is 0. Derivative here is a1. Derivative of z squared is 2z, all right, and so forth. Now, if I evaluate this for z equals 0, replace z with 0, here you get derivative evaluated at 0. On the right-hand side, all these terms will vanish. You will get a1. So here is a1. So what is a1? A1 is just derivative evaluated at 0, and no way we can have two different numbers here, right? You continue this, of course. Next time, if double prime, and you evaluate again in 0, so you get 2a2 is if double prime at 0. Here is a2. You do it one more time. Here is a3. In general, you will have a sub n. Okay? N's derivative evaluated as 0 divided by n factorial. So those are the coefficients. Okay? So, although I sort of demonstrated uniqueness by using the center being 0, we could have had the center at somewhere else. For example, I could have this power series, the center being let's say alpha. And going from 0 to infinity. With the same argument, if you replace z with alpha, oh, let me write a few terms of, for n equals 0, you get a0. For n equal 1, you get a1, z minus alpha, and so forth. If you evaluate, replace z by alpha, everything here will vanish. So a1 is f of alpha. A2, with the same argument, is f prime. Oh, this is a0, sorry. A0 is f of alpha. A1 is f prime of alpha, and so forth. In general, you will find that a sub n in this case is, in fact, the nth derivative of f evaluated at alpha instead of 0 alpha divided by n factor. Okay? So that proves the sort of uniqueness. If we can find power series for a function, we are sure that that power series is unique. All right. Well, that gives us a very interesting tool, very interesting tool. And by using the Taylor's theorem that I talked about it last time, I just mentioned it without proof, and still I'm going to mention it here without proof. If you are interested in its proof, please read. It is in the book, read through it. And if you have any question, you have some ambiguity, you cannot understand what's going on, then ask me. I will be more than happy to discuss with you. So Taylor series is this. It says the function has to be analytic. Analytic means derivative exists everywhere in this domain. So there is no bad point in this domain. If there is no bad point and alpha is in here, you can have a power series centered at alpha. And that power series centered at alpha. The question always is, what about this? AN. What is AN? In fact, AN is going to be right here. Remember, we said in the uniqueness, AN is the nth derivative evaluated at alpha n factorial. But Using the Cauchy's integral formula for derivative, the nth derivative evaluated at alpha is actually right here. Okay, so a sub n not only can be expressed in this fashion, but theoretically also can be expressed in integration format. So that is Taylor series. But remember, there's a condition here. The function has to be analytic in this simply connected domain. There's no hole in here. There's no bad point here, right? Of course. Well, the question, what if we have a bad point there? If there is a bad point, then we will use another theorem, which is called Laurent series. And still we are going to have a power series, but in that power series, we are going to have also negative powers of z minus alpha. Here, it is always positive powers of z minus alpha, right? N equals 0 gives us a constant, but after that, all positive powers of z minus alpha. But if there is a bad point there, which we will discuss that in next chapter, instead of Taylor series, it will be Laurent series, which is quite similar to this one, though. But we are going to have also the negative powers of z minus alpha. Anyways, so if alpha is 0, the center is 0. We call it Maclaurin series. That's fine. It's Maclaurin series. Now we will apply this Taylor series to find a power series representation for some functions. Here is e to the z. Last time I talked about e to the z, right? So this is the to the n. Okay. Make sure that z looks nice. Z to the n divided by n factor. And the reason for this one, if I want to have power series using Taylor's theorem, I need the nth derivative of e to the z evaluated at 0, but nth derivative is e to the z itself. You evaluate at 0, you get 1 here, so 1 over n factorial will be right there, and z to the n, okay? We do the same thing for cosine. If we go through this coefficient, the nth derivative evaluated at 0, right? This one, I'm writing the Maclaurin series. This is going to be the coefficient, okay? For sine z, all right, the same thing. We can go through the same process, at least for these 3 functions, all right? We go through the same process and we find the Maclaurin series of these functions. There is another one, though. And that is the geometric series. Remember geometric series? Geometric series is this. Right? It converges if and only if modulus of z is less than 1. Now, from this point on, we can use these guys. For example, having this one, I can replace z by negative z. Here I get 1 over 1 plus z. And here I'll get this series. So this is the shortcut for finding the power series representation of this function. Okay, power series representation. I already know this. Just replace z by negative z. That's what you get. Why can I do this? What is the rationale? The rationale is we just noticed that power series representation of a function is unique. So, being unique doesn't matter how I find the power series as long as I'm doing the right thing, of course. All right. Since power series representation is unique, I can use shortcuts. Okay, we can use shortcuts. And today I'm going to give you some examples of these shortcuts. Okay, so that's the same thing. The Taylor series, and all right. Going for a shortcut. Why not? Let's look at this one. I want to write the Taylor series of e to the z with center at 2i. What does it mean? It means you need to have a power series in powers of z minus 2i. Okay? Oh, here is how I will use the shortcut. I'll say, look, e to the z e to the z, I can write in the exponent part, add 2i and subtract 2i. Oh, I want powers of z minus 2i, right? So we will keep this portion and write it in this fashion. This is a constant. All right, keep it as a constant. But here, I know that the e to the w is this. Now you replace and this is good for all values of W, right? This power series converges because e to the z is an entire function. Same thing for sine z and cosine z. So replace W by z minus 2i. You will get this one. So this portion, replacing z by z minus 2i, is right here. And this is a constant. So here is the power series or Taylor series of e to the z, with center being 2i. Okay? Any comment? Any question? Any question? Well, the topic is pretty familiar because you have seen these type of things in calculus. Right. So here comes another example. We already know this geometric series. It converges if and only if modulus of z is less than 1. Now I want to find the Maclaurin series of this guy, this function. Maclaurin series means in powers of z. When you are doing in powers of z, we don't have any problem with this guy. It's already in powers of z. So the question is, what about this part? What about this part? Well, that is when we use that geometric series. Here is the geometric series. Replace z by negative z. You'll get this one. Now you replace z by z squared. You get this one. So after having this portion in powers of z, now you multiply by z cubed, that you get g of z. So g of z is right here. You multiply by z cubed. So z cubed goes inside. You get 2n plus 3. All right. So a very good example, the process of using shortcuts. All right. Again, what is the rationale? Why can't we do this? Because the power series of a function is unique. All right, it is unique. Now, if I can be creative and find the power series in this fashion, why not? I don't have to go through the Taylor series on this. I mean, this is Taylor series. I don't have to go ahead and find the nth derivative and then evaluate the nth derivative at 0 and do this thing. If I can find a shortcut, why not? Let's do it. Okay. All right. Let's see if I have another example for you. I do. Here is another one. I want to write the Maclaurin series of this function. z to the 4 divided by 1 minus z squared. Well, Maclaurin series, again, means in powers of z. When you are writing in powers of z, we don't have any problem with this. It is already in power of z. This is the part that we need to work on it. Well, doing shortcut again. I already know the geometric series. And geometric series converges absolutely when modulus of z is less than 1, which means the unit disk, inside unit disk, this is a continuous, beautiful function, has derivative, has integral, whatever, all right? So why don't we take derivative of both sides then? Derivative of this side, using quotient rule, is this. Derivative of this one is 1, 2z, 3z squared, and so forth. Okay? So I already found the power series or Maclaurin series of this guy. It's right there. Now multiply by z to the 4. This is what you get. Okay? This is what we get. Any comment? Any question? Well, let me give you another one just to make sure that you feel comfortable in writing either Maclaurin series or power series or Taylor series. We have different phrases to apply. So let's do this one. Write the Taylor series of this with center being 2i. Center 2i means you want to have a power series representation of this guy in powers of z minus 2i. This is the center. Now, here is what we do. We want in powers of z minus 2i. Well, going back to geometric series. I already have here geometric series, right? This is geometric series. But I want in powers of z minus 2i. So I will add 2i and subtract 2i in denominator. So if I added 2i and subtracted 2i. If you factor negative, you get z minus 2i. So somehow z minus 2i, we made z minus 2i appear. But if I want to make use of geometric series, I need to somehow make this one look like 1 over 1 minus something, right? If I want to use this geometric series. This is the format, 1 over 1 minus something. That is when you factor 1 minus 2i from denominator. If I factor 1 minus 2i, here I get 1. Here, this will be divided by 1 minus 2i, okay? So, this is what I meant by you try to make it in the form of 1 over 1 minus something. Now you can use geometric series right here. This is a constant, is right here. And this part will be just this guy to the end, geometric series. And there is a fine point here. We can do this if and only if modulus of this guy be less than 1. All right. So modulus of this guy less than 1 means modulus of numerator divided by modulus of denominator, all right, means this. But modulus of this one is the square root of 5. So this power series representation, we found g of z is this. This is a constant, z minus 2i to the n. We wrote it in the powers of z minus 2i, but remember, this is valid if and only if this guy be less than. So the radius of convergency is the square root of 5. The center is 2i. Okay? So this is actually a beautiful, beautiful example that I just gave to you that in a way, the highlight of today's lecture, that how do we write the power series x by using shortcut. Any comment, any question about this example or today's lecture? Any comment? Okay, I don't see any question. So pretty much you're now able to do all the problems of 15.3 and possibly 15.4. But since I'm going to follow the schedule, that the spreadsheet, for the time being, please go ahead and read 15.3 and also 15.4, why not? And start doing the example. Yes, Del Dodson is asking a very good question. We are concerned about the radius of convergency. That is why we always will try to find that radius of convergency. What happens outside radius of convergency is very simple. The series diverges, all right? The series diverges. So, yeah, when the function is an entire function, we don't have any problem with that because the radius of convergency will be infinity, like e to the z. e to the z, its power series expansion is always this. Let's see. I had it. I have it here. Let me show you. So this is e to the z. We don't have any problem with it. Okay. Let me take it right. E to the z. It converges everywhere. Everywhere. It's the image is a little blur. I'm trying to make it sharper. Okay, see, it converges everywhere. We are not really concerned about this one. So the radius of convergence is infinity. Same thing with cosine z. Those are entire functions. This series, these three, they converge everywhere. So the radius of convergence is infinity. But when it comes to this guy, this has a bad point. And that point is z equal 1. So we got to be careful about this, all right? And it converges, the radius of convergence here is 1. What happens outside? It diverges, all right? Just using the generalized ratio test. Generalized ratio test says if L is less than 1, it converges absolutely. But if L is bigger than 1, it diverges. And in this case, if you go through the generalized ratio test that we did, the limit L is this, z. So if this is bigger than 1, this series diverges. Okay, good. Good question. Yeah. We are concerned about outside of the radius of convergency. We know that outside it diverges. We are more comfortable to work with the series inside the radius of convergence. Any other comment, question? No question. All right. If you don't have any question, then please go ahead and study hard. Remember, you on the day of test number 2, you are supposed to know this stuff and take the test. So you are not supposed to study just that day and the test, take the test. No, it doesn't work that way. So right now you have the opportunity to look at your notes, to look at your text and learn the material. And on the day of test, just instead of 3 hours, you can do it in 1 hour, as a lot of you did. Okay. All right. Have a good day, everybody. I will see you on Thursday. Bye-bye now. Thank you, Jason. Thank you, Matthew, Corey, Del Dotson. Thank you. Thank you, Fox.